In this video, we are going to continue talking about the topics of chapter 2. Now we're going to focus on hydrogen bonds specifically. Now, one of the things is that if we look at water molecules interacting with themselves, okay, because a water molecule has oxygen, hydrogen bonds, and it meets the requirements for hydrogen bonding events, then it makes sense that the water molecule, when it interacts with itself, it actually does it through hydrogen bonding. Now, understand that the properties that we see of water have to do in part because of these hydrogen bonding events that occur between water molecules. Now, when we compare molecules of similar size in terms of molecular weight with water, so for example, ammonia, methane, you can see that they have on average around the same molecular weight. But it is very interesting to see why is it that, for example, when we compare the melting point or the boiling point of water, why is it so different than those molecules? Well, that has to do specifically with the hydrogen bonding events. As you can see on the molecule that we have, there are a number of hydrogen bonding events that can happen with water and its neighbors. How many, you would ask yourself? Well, each water molecule participates in 4 hydrogen bonding events. Okay, so understand that here is illustrated as full positives or full negatives, but understand that these are partial charges. So these are delta pluses or delta minus. So I just wanted to specify that it's not full charges but partial charges. So when we look at one water molecule, understand that oxygen, even though I haven't illustrated before, is going to have 2 lone pairs because that is the correct Lewis dot structure for it. So when we have the interaction of water molecules with other water molecules surrounding it, the 4 hydrogen bonds that are present between those molecules come from a hydrogen atom. I'm just going to highlight them. A hydrogen atom interacting with the oxygen of a neighboring molecule. So each one of them does that. That's where 2 come from. The other ones are because of the oxygen atom of the center water molecule interacts with hydrogens of neighboring water molecules. That's where 1, 2, 3, 4 hydrogen events come from in water molecules. Now, understand that hydrogen bonding events are not exclusive to water. We illustrated in the previous video how ammonia can also have hydrogen bonding events. So when we compare hydrogen bonding events between molecules that are known to have hydrogen bonding between them, we can see that water has a greater number compared to, for example, hydrogen fluoride or hydrogen monofluoride. Remember that if it's aqueous, that's fluoric acid. So I'm just giving all the names. Or if we compare it to ammonia, understand that the hydrogen bonding events between the molecules to themselves are going to be different from the ones of water. Let's look at, for example, hydrogen monofluoride, which is HF. When we look at a molecule of HF interacting with itself, one of the things that we can see that in between the molecules, specifically, we're going to have hydrogen bonding acceptors, specifically, and we can also have hydrogen bonding donors. This one is not illustrated, but I'm just going to highlight it. So this is also a donor. Okay. So a hydrogen bond donor is going to be the hydrogen that is going to interact with the negative charge of a neighboring molecule. Let me just write that definition. A donor is a hydrogen atom that interacts with delta minus of a molecule. A hydrogen acceptor, just to define it, is going to be an atom with a delta minus. In this case, we're going to see that the delta minus is because of the electrons that interacts with a hydrogen atom bonded to either fluorine or oxygen or nitrogen. I just want to specify what it constitutes an acceptor and what constitutes a donor. So when we look specifically at the molecule of HF, I'm just going to highlight it as a whole. In the molecule of HF interacting with itself, we can see that the hydrogen bonding events, specifically within one molecule, are going to be less than the ones in water, because HF is limited by the number of hydrogen atoms that it has and also the lone pairs that are present on that fluorine. If we look specifically at ammonia, which I'm going to be highlighting in yellow, you can see that ammonia, through the nitrogen, which is the atom that can act as an acceptor, because that nitrogen only has one lone pair, then it only has one acceptor side. Now, if we look at how many donor sides it has 3, each of the hydrogen atoms. But because when we look at 2 ammonia molecules, only one acceptor side compared to 3 donor sides, that's why we see also a limited number of hydrogen bonding events. When we look at what happens in water, in one molecule of water, we're going to have 2 acceptors and 2 donor sides. So because, again, it has more of those sites, more hydrogen bonding interactions can occur. Now, in this course, understand that the interactions of biomolecules with water are going to be defined with different terminology. And specifically here, we can see that there are 3 different interactions that can occur between water and biomolecules, and we're going to define them. The first one is defined as a hydrophilic. Hydrophilic stands for, quote unquote, water loving. What does that mean? If we have a portion of a molecule or a part of a biomolecule that is hydrophilic, that means that it's going to be able to interact with water, or it can dissolve in water. Whenever we have a portion of a biomolecule that is hydrophobic, hydrophobic stands for water fearing. Okay, so those molecules or those portions of biomolecules are not going to like to interact with water, so they tend not to dissolve in it. Now, we have something very particular. We have also a third type of interaction with water and biomolecules, and that's an amphipathic interaction. So molecules are considered amphipathic when they have not only hydrophobic, but they also have hydrophilic portions to them. Okay, so when we think of these, we can look at molecules like soaps. In a soap, once we talk about the lipid chapter in this course, we are going to talk at those at the molecular level, but understand for now that a soap, which actually comes from being the carboxylate of a carboxylic acid. So they are the result of saponification. Which is base hydrolysis of a carboxylic acid. They are amphipathic because understand that this molecule will have a polar side, which is known as a polar head. In this case, is going to be the carbon that is double bonded with oxygen and single bonded with oxygen. So in the molecule will be given by these atoms. And the molecule is also going to have a non-polar side, which is going to be given by these carbon-hydrogen bonds at the end. I'm just going to highlight them in the molecule. So you can envision that in an amphipathic molecule, when it interacts with water, then the polar head is the portion that interacts with water. Now, understand that hydrogen bonding also plays a role in the behavior of water as a solvent. And when we look at it specifically in terms of the functional groups that are important in biochemistry, these are the different type of interactions that can happen through hydrogen bonding of water with different functional groups. Okay, so let's say that we have a hydroxyl group of an alcohol in water. One of the things that we observe is that alcohol, the hydrogen can act as a donor, and then the oxygen in the water can act as an acceptor. But I'm just going to write and vice versa, because you can also observe when you have an alcohol that the opposite is true, that this oxygen atom, let me do it in a different color. These green dotted lines are going to be the hydrogen bonding event, can interact with the hydrogen in a water molecule. So understand that the hydroxy group that is part of the alcohol not only can act as a hydrogen bond donor, but it can also act as an acceptor. That's why I write vice versa. And then the water molecule, the oxygen can act as an acceptor, but then the hydrogen in the water can also act as a donor. So understand that when it comes to hydroxyl groups and water, it can do both. Now, when we have a carbonyl group, it can come from a ketone, it can come from an aldehyde. There's many functional groups that have carbonyl groups. Understand that there it is limited. The hydrogen bond acceptor is going to be specifically the oxygen atom in your carbonyl. The hydrogen bond donor is going to be one of the hydrogen atoms in the water. So that is going to be the interaction, okay, between something that has a carbonyl and a water molecule, where the oxygen in the carbonyl is going to be the hydrogen bond acceptor. The hydrogen in the water is going to be the hydrogen bond donor. In this case, understand that the reason why I didn't write vice versa is because the oxygen atom in the carbonyl does not have a hydrogen. Lastly, when we have an amino group, meaning you have an amine, and they interact with water, understand that here we have shown specifically here how the hydrogen bond donor is going to be specifically one of the hydrogen atoms bonded to the nitrogen, and the hydrogen bond acceptor is going to be the oxygen in the water. Well, in this case, understand, because nitrogen is electronegative, the nitrogen atom can also be interacting one of the hydrogens in the water. So understand that the amine, which is what is represented there, can also act as an acceptor. So that means that the water molecule can also act as a hydrogen bond donor. So that's what I mean with the vice versa. Okay? So understand that in general, the most important functional groups that you should understand these three interactions are in terms of alcohols, which is explained in the first diagram, amines, which is explained in the last diagram. Think about how carboxylic acids will be interacting with water based on the rules explained. Think about how esters, aldehydes, and ketones will interact through hydrogen bonds with water. That is going to be part of the things that I want you to rationalize for the exam. Now, understand that there are some biologically important hydrogen bonds. And as you can see here, they are summarized in table 2.5. This is just illustrating examples of the major types of hydrogen bonds found in biological molecules. And as you can see, it's just showing on the left side the bonding arrangement, and on the right side the molecules where bonds occur. Okay, so it's giving you examples that we are going to see throughout the semester of biomolecules with water. Now, one of the book problems that I want you guys to understand is, if you are given a molecule, can you rationalize based on the rules given on previous slides of how many water molecules will be interacting with a particular molecule through hydrogen bonding? And here, for example, we have the molecule of glucose. Problem 17 in the textbook reads, how many water molecules could hydrogen bond directly to the following molecule? In order to do these problems, remember that you have to apply the rules for the functional groups given in previous slides. But here specifically, what I want you to think about is that in order for hydrogen bonds to occur, we need to have a hydrogen bonded to anything fun, either fluorine or oxygen or nitrogen. When we look at our molecule of glucose, we see that for that we have 1, 2, 3, 4, and 5. Now, the rule of thumb is that if you have a hydroxyl group, there's going to be an interaction with 3 water molecules. So every OH is going to interact with 3 water molecules. How does this occur? I'm just going to take a snapshot of this and then just illustrate the OH group. I'm going to write the lone pairs on that hydroxy group. And this is how a single hydroxy group, and here the squiggly line is going to represent the rest of the molecule. So if we have a hydroxy group, the reason why it interacts with 3 water molecules is because specifically we see that the oxygen can interact with hydrogen in a water molecule, each of them, so each lone pair. I'm just going to write these dotted lines. So these are the interactions with the oxygen atom in the hydroxy group with the water. So as you can see, that oxygen atom is going to be acting as a hydrogen bond acceptor. Okay. And then the oxygen atom of the water can interact with the hydrogen atom in the hydroxy, in which then that hydroxy group is interacting as a hydrogen bond donor. So that's the interaction, the three water molecules interactions. Now, understand that so far we have three there, three there, three here, okay? So at first you will say, oh, they're 15. Well, specifically in this molecule, we also have an oxygen atom that has lone pairs. So even though it's not bonded directly to hydrogen, it can actually act as a hydrogen bond acceptor. So with how many water molecules can those lone pairs interact? With two of them. So let me just, so this can interact with the hydrogens in two molecules of water. So whenever you're doing a problem like this, always look at atoms in which you have fluorine, oxygen, or nitrogen bonded to hydrogens, and also at the fluorine, oxygen, and nitrogen. Take into account how many lone pairs are going to be present in those atoms and the number of lone pairs. Each lone pair is going to act as a hydrogen bond acceptor. Okay? And as you can see, that worked out for the hydroxy group or also for the oxygen atom here. So the final answer for this problem is 17 water molecules are going to be interacting with glucose in this case through hydrogen bonding events.